You may think black holes are scary. They are. But once you learn what this object in the space can do, black holes won't be that frightening anymore. These things can destroy our ozone layer and probably kill all life on Earth. In this short documentary, we dive deep into the cosmic anomaly of magnetars. We discuss its effects on Earth, how magnetars has already damaged us, and how near are we to such a monster. Magnetars are a remarkable class of neutron stars, which are extremely dense remnants of massive stars that have undergone supernova explosions. What sets magnetars apart from other neutron stars is their incredibly strong magnetic fields. In fact, magnetars possess the strongest known magnetic fields in the universe, with surface magnetic field strengths that can reach up to 1 billion times stronger than those of typical neutron stars. The origin of such intense magnetic fields in magnetars is still a subject of scientific investigation, but it is believed that they arise from the processes occurring during the supernova explosion that gives birth to the neutron star. As the core of the massive star collapses under its own gravity, the conservation of angular momentum causes the core to spin rapidly. This rapid rotation can amplify any existing magnetic fields, creating the extreme magnetic strength seen in magnetars. The details of how this amplification occurs are complex and not yet fully understood. The magnetic fields of magnetars are so powerful that they have profound effects on the behavior of these objects. They lead to a range of remarkable and often violent phenomena. One of the most striking is the emission of intense bursts of X-rays and gamma rays. These bursts can be triggered by a variety of mechanisms, including the rearrangement of the magnetic field lines in a process known as magnetic reconnection. These outbursts of energy make magnetars some of the brightest X-ray sources in the sky. The immense magnetic forces on magnetars also cause them to have highly active surfaces. The magnetic stresses can generate enormous seismic activity, creating quakes or starquakes that result in the release of energy in the form of X-rays. These starquakes can alter the X-ray emission patterns and provide astronomers with insights into the interior structure and magnetic field geometry of magnetars. The intense magnetic fields of magnetars also have an impact on their surroundings. They can influence the behavior of nearby charged particles and produce powerful winds of particles moving at nearly the speed of light. These winds interact with the surrounding interstellar medium and can have significant effects on the environment of the magnetar. Magnetars are a variation of neutron stars, and they somehow manage to be even scarier. Neutron stars already have extremely strong magnetic fields, about 2 trillion times more powerful than Earth's. Yet, magnetars have magnetic fields 1,000 times stronger than that. Yeah, that's a pretty intense field. Magnetars are not just insanely powerful, they're also very, very dangerous. If you were a mere 1,000 kilometers from a magnetar, your entire body would dissolve as the magnetic field rearranged the sequence of atoms in your body. In addition to their terrifying magnetic powers, magnetars also have something called starquakes, which function similarly to earthquakes here on Earth, except with much more intense results. A crack in the crust of a magnetar is responsible for the brightest light we've ever observed from space. And if a magnetar was closer to us, like 10 light years away, and blasted us with the radiation from a starquake, it would destroy our ozone layer and probably kill all life on Earth. As an example of extreme behavior, in 2004, a flare on the surface of a magnetar compressed the magnetic field of the Earth from a distance of 50,000 light years. When you consider that a neutron star is about the size of a city, a recent revision of neutron star size puts it at maximum of 15 miles or 24 kilometers across, but may contain 1.5 times the mass of our Sun. It is incredible that such a tiny object can generate enough energy to affect others at such a vast distance. Astrophysicists do not yet know exactly how a magnetar generates its stupendous magnetic field. However, it probably relates to the incredible density of neutron stars and their bizarre interiors. Just one sugar cube-sized amount of neutron star material would weigh 1 billion tons on the Earth, about the same as an average mountain. The magnetic field of a magnetar may be caused by a neutron star's interior, thought to be made up of neutrons, quarks, and exotic states of matter such as Bose-Einstein condensates, becoming a superconducting fluid. Thus, when the star rotates, it would behave like a huge dynamo, generating an immense magnetic field. Or, the field may simply have its origins in its progenitor star, the kind of star it was before it became a neutron star, which may have had an unusually strong magnetic field. In an effort to solve this enigma, astronomers launched an instrument called the Neutron Star Interior Composition Explorer, NICER, to the International Space Station in 2017. Its specific goal is to determine what exactly is inside neutron stars. The first event that originated from a magnetar showed up in 1979, although at that time astronomers did not identify the activity as belonging to a separate class of objects. It occurred when two Russian spacecraft suddenly observed a huge blast of gamma radiation in their detectors. Readings on both the probes went up from a normal 100 counts per second to over 200,000 counts a second in a fraction of a millisecond. This was more than 100 times the energy of any extrasolar gamma ray burst previously detected. 5 satellites and 2 observatories also registered it, as the wave of gamma radiation traveled through the solar system. When astronomers tracked down where the burst had originated, it corresponded to the location of a known supernova in the Large Magellanic Cloud. The object that generated this huge wave of gamma radiation has since repeated the event, making it the first known soft gamma repeater. Nobody knew the exact cause of the event back in 1979. It wasn't until 2008 that astronomers identified a neutron star that acted like a pulsar and emitted magnetically powered bursts. This event confirmed magnetars to be a rare type of neutron star. There are only 31 confirmed magnetars in total, out of around 3,000 known neutron stars. This is an indication of their rarity. Magnetars have also emerged as prime candidates for causing fast radio bursts, or FRBs, those enigmatic millisecond-long pulses of radio waves that carry as much energy as our sun releases in a year. Up until recently, astronomers thought all FRBs were extragalactic in nature, but in April 2020, they detected an FRB coming from inside our own Milky Way galaxy. Astronomers pinned its location down to a known magnetar, SGR 19352-154. In May 2021, NASA reported that the Hubble Space Telescope had identified 4 FRBs in the spiral arms of distant galaxies. These are thought to have originated from magnetars. This was an important step forward, as up until recently the exact location of FRBs proved very difficult to pin down, mostly due to their short duration of just 1,000th of a second. Furthermore, most FRBs do not repeat, making their location on the sky and distance difficult to identify. How and why a magnetar might generate an FRB is not yet known. A team of astronomers has directly measured the distance to a magnetar. It's called XTEJ 1810197 and was discovered in 2003. Of the roughly 30 known magnetars, it's one of the few that emits radio pulses, making it a pulsar. It emits beams of energy like a lighthouse, and as the neutron star rotates, these beams sweep over the Earth, which we see as a sudden and short blip of energy. It means it can be observed using radio telescopes, and there is a technique called interferometry that essentially connects telescopes from across the world, mimicking the resolution of a single telescope the size of Earth. This allows for extremely precise measurements of an object's position. They observed it over a period of 1.5 years, and over that time, the Earth moved around the Sun by a known amount. They could detect the apparent motion of the magnetar compared to much more distant objects, and find its distance. Turns out, XTEJ 1810197 is about 8,100 light-years away, making it the closest known magnetar. Yeah, it is pretty far, right? Actually, no. In the cosmic scale of things, this magnetar is quite close to us. But don't worry, while magnetars are extreme and enigmatic objects, the chances of them directly impacting us are very remote due to their distances and the protective features of Earth's environment. Scientists continue to study magnetars to unravel the mysteries they hold and to gain insights into the fundamental nature of matter and the universe. If you're as captivated by the mysteries of space as we are, consider joining the journey with Astronovium. Delve into the universe with us as we explore its wonders through captivating short documentaries. Don't forget to give us a thumbs up and subscribe to our channel to stay connected with the latest revelations from the cosmos.